Hello, lovely humans, Jen Foxbot here. In today's episode of Math Mondays, we are continuing our machine learning exploration by looking at the second topic in applying gradient descent. Yay! Okay, so when we are building a machine learning algorithm, specifically with gradient descent, there are a few different things that we can tweak and tinker with to get the best results that we can. So we talked about scaling our features, and now we're going to talk about the learning rate. Woo! So let's back up a little bit. First of all, there are two crucial things that we need to do when we apply gradient descent. Number one is make sure gradient descent is working as expected. And number two, figuring out how to choose an appropriate value for the learning rate. Okay, I keep saying this term learning rate. What does that actually mean? Let's look at the equation for gradient descent. So the goal of gradient descent is to find parameters for a polynomial function. Let's say it's y equals mx plus b. In this case, our two parameters are going to be theta 1 is going to be m, and theta naught or theta 0 is going to be b. In this case, we have two parameters. Most of our data sets are going to be much more complicated and have higher orders of magnitude of x, like x cubed, etc. And so we'll have more parameters associated with each of these terms. So we want to find the parameters that best fit our data set, which requires us to make some guesses, find the difference between the guess and our prediction, and then update that. And so the algorithm equation can be summed up as like the new parameter, theta subscript j, is defined as or is equal to the previous parameter minus alpha, which is our learning rate, times the partial derivative with respect to our parameter. Oh, sneeze from chalk dust. Oh, excuse me. Of the cost function, j of theta. And so our cost function is that difference, how far away the actual values are from our predicted values. So this is the learning rate, and we have some control over what this is. And if we look at it from a mathematical perspective, we can think of this as a scaling factor. Basically, how much do we want to move from this previous parameter? In other words, if the learning rate is really, really big, we are going to take a really big step. We're going to subtract a big number from this parameter and get a very different number. Like, for example, if this is 10 and this is 1, we're going to subtract 10 from this previous parameter. But if the learning rate is small, let's say it's 1, 1 times 1 is 1, we're going to just subtract 1 from this parameter. So even though we can't really control the value of this, we can change how big of steps we're taking in between iterations with this learning rate. So the first thing we want to do to figure out if gradient descent is working, and thus what value we should pick for the learning rate, is to plot the cost function over the number of iterations. So this is one of the really, really important plots. I think that is a really crooked line. This is one of the really important plots to make when you're doing machine learning. You're using Python, you can just create a plot and spit it out so you actually can visualize what's going on. So on the x-axis, you want number of iterations, and on the y-axis, you want the cost function, so j of theta. If gradient descent is working properly, you'll get a curve that looks like this, where it is an asymptote that converges towards 0. So you're probably going to want to pick a value, a number of iterations somewhere between here and here, where it's very, very close to 0. How you define how close to 0 is good enough is depending on your situation. So for example, if you're applying machine learning to detect cancer in a tumor based on images or something like that, you're going to want a really, really accurate machine learning algorithm. Makes sense. There's a high cost for a false negative, right? But if you're building a machine learning model to tell you to predict what the temperature is going to be tomorrow, it's probably okay if you're off by a few degrees, because personally, my body can't really tell the difference between 65 degrees and 62 degrees. So you could probably get away with fewer iterations. It might be helpful to define for your particular scenario what it means to converge. So let's say you are satisfied if your cost function has a value of 10 to the negative 3. And so you can kind of set an automated converge number, where basically you're like, this is close enough to 0, and that works for me. Okay, so how do we tell if the cost function or if gradient descent is not working? Okay, so this is where you're going to get different looking curves. You might get something like this. This is really bad because it means that your cost function is increasing. In other words, your predicted values are getting farther and farther apart from the actual values. You might also get a curve that looks like this or something like that, where it's decreasing and then it's going up, and it kind of is oscillating about an average value. In both of these situations, what you're going to want to do is draw little arrows, and I'm going to write it in red because it's really important. Need smaller learning rate. Boop. So by plotting the cost function over the number of iterations and seeing how the cost function is changing over time, that will tell you what you need to change for the learning rate, or I should say how you need to change it. So for a sufficiently small learning rate, your cost function should decrease for each iteration of gradient descent. But if it's too small, it's going to take forever, and we don't have it forever, right? All of our lives are finite. We want to make the best use of our time as possible, and we don't want to waste our time picking a really, 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 really small learning rate. So even though it would probably get us there, our time is valuable, and our computer's time is valuable. So to choose a learning rate, the expert himself, Andrew Ng, recommends just choosing a reasonable value and adjusting that, and then plotting the cost function over the number of iterations and seeing how it changes. Some of the values that Andrew Ng suggests starting with are, within like 0. Start with, okay, 0.001. Oh, we're running into number of iterations. That's okay. 0.003. So increase by a factor of 3. And then maybe increase by a factor of 10. So 0.01, 0.03, 0.1, 0.3, 1, 3, etc. And what Andrew Ng recommends is kind of, rather than going in order, start with a fairly large learning rate, like maybe you start with 1, and then see what happens when you jump to 10 to the negative 3 or 10 to the negative 4. And then kind of like bounce back and forth until you start to converge on an ideal learning rate. So that way you can more quickly find if the learning rate is working for your given scenario or not. Cool. Okay. So I hope that that's helpful. There's not really an exact science to this. So the key here is to have some visualizations to help you figure out what's going on and find a reasonable range. It doesn't have to be perfect. And again, just keep in mind what your specific application is and go with that. Or I should say, do what you need to do for your application. Okay, please let me know if you have any questions about the learning rate or making these plots and why you should make them. We are going to continue topics in machine learning next week, so yay! I'll see you then. Thank you for watching, friends, and have a wonderful rest of your week. Bye!